Hello students, I hope you are good, well and fine, and today we will be continuing our discussion on the topic of relation functions and NCERT exercise 1.1. As we already saw the solution for the question 1, now it's time to see for question 2. Okay, so let's solve with me. So show that the relation R in the set. So the relation is in the set of real numbers are defined as, so we defined our relation in this way, and what we need to show here is it is neither reflexive nor symmetric and nor transitive. So for reflexivity, if you recall, for reflexive relation, what we need for reflexive relation, we need that if you take any element in if my relation is from A to B, that means R is my subset of A cross B. Yes, then take any element in this set, in the first set of the Cartesian product, which is this. Take any element in this set A here, okay, and taking any element, say I am taking the element A, then A comma A must be in relation R. That means in mathematical way of representation is A comma A belongs to R for every A belongs to A. Okay, so this is our definition for reflexive relation. Now for symmetric relation, what we need? We need if A comma B belongs to the relation R. So we need this condition to be hold. Then B comma A must also belongs to R for every A B belongs to, where A belongs to A and B belongs to B. Okay, I hope this is clear to you. And for transitivity, for transitive relation, as the name suggests, transitive, the things are getting transferred here. So we have two conditions, AB and BC belongs to R. Okay, the main point to keep in mind is this, that the second element in this pair is the same as the first element in this pair. Okay, so if AB belongs to the relation and BC also belongs to the same relation, then the things get transferred to C. As you can see, A goes to B and B goes to C, then A goes to C. So if A goes to C, if this also happens, that means A comma C pair belongs to R, then we say that it is my transitive relation. Okay, I hope the definitions are very clear to you. Let's jump to our question. So in here, let's check for reflexive condition, reflexive. So does A comma A belongs to the relation R? Does A comma A belongs to the relation R for every A belongs to the set of real numbers? Does this happens? Let's take take a real number. Suppose I'm taking 2. So 2 comma 2, by definition, if it belongs in the relation R, this means 2. So A, this element must be less than equal to this square of the second element. So the second element is here, so square of this. So 2 is less than equal to 4. Yes, it seems like it's going to be true, but no. Why? Because we are talking about A such that A belongs to the set of real numbers. In real numbers, if you recall, 1 upon 10 is 1 upon 10 is greater than 1 upon 100. Is it so? Yes. So 1 upon 10 is greater than 1 upon 100, and we know 1 upon 10 is greater than equals to 1 upon 10 square. Yes, it is true. Yes. But here the condition says A is less than equal to, for reflexivity, here A is less than equal to A square. But here we have seen that A is greater than equals to A square. So I can say that A comma A does not belongs to R for every A belongs to R. Yes, as we have seen an example of it. If you take A as 1 by 10 and A square gets 1 by 100, and we all know that A is not less than equal to A square here. As you can see that A is 1 by 10 and 1 by 100, we know that it is not less than equals to. It is the symbol will be this, the greater than. Okay, I hope the reason is very clear to you. So this relation is not my reflexive, as given in the question we need to show. So we showed that it is not reflexive. Okay. Now what? Now let's check for symmetricity. Okay, so is this symmetric? As we already given with that it is neither reflexive, neither symmetric, and neither transitive. So the thing we need to find here is the contradictory example which doesn't obey the definition for the relation to be satisfied. Okay, so symmetric relation, let's try to prove that it is not symmetric. Okay, how we are going to do? Quite easy. If you recall the symmetric definition, if A comma B belongs to R, then B comma A must also belongs to the relation R. Okay, so this R is the relation R. Okay, relation R. Okay, so if this is not symmetric, this means if A comma B belongs to the relation R, then B comma A does not belongs to relation R. Yes, by definition we can say if not symmetric, what we need to show? If this happens, then this might not happen. Means there exists some A comma B pair such that the B comma A pair is not in the relation. Okay, so let's see. Can we find out? Yes, we can quite easily. How? If you take A to be say 3 and say let's take B. What can you take as B? As 10. Okay, now A is less than equal to B square. Is this true? That means 3 comma 10, A, we know 3 is less than 10 square, which is 100. It is true? Yes. This means 3 comma 10 belongs to R. Does 10 comma 3 belongs to R? Let's see. If 10 comma 3 belongs to R, then 10 must be less than equals to 3 square by definition of the relation. Okay. So is this true? No. As you can see, 10 is not less than equal to 9. It is greater. So this means we have seen A comma B belongs to the relation, but not B comma A belongs to the relation, as you can easily see. So this is not symmetric. So it is also not symmetric. Okay. Now what? Now the interesting part, we have arrived that how we are going to show that it is not transitive. So quite easy. If we know the definition for transitivity. Okay. So in transitivity, if you recall, what is our definition for transitivity? Transitive relation. If AB and BC both belongs to the relation R, okay, then A comma C also belongs to the relation R for every A, B, C belongs to real numbers. Yes? Okay. So not transitive, to prove not transitive, we need to show that A and B, AB and BC both belongs to the relation R, but AC does not belongs to the relation R. Yes, there exists some AC which follows this thing. Okay. So let's see, is there any? As you can see that it is already given that it is neither transitive. So we need to just find out what A, B, C we are talking about. So let's see. Okay. So quite easy. How? Why I am saying it is quite easy? That take A as 3, B as 4, and I will take C according to them, as you can see. How? Does AB belongs to R? Yes. Why? Because 3 is less than equals to, let's take B as 2, not 4, just take 2. So this means 2 square. Yes. 3 comma 2 belongs to R because 3 is less than equals to 2 square, which is 4. Is it true? Yes, indeed it is true. Now taking C such way that BC belongs to R. So I am taking B is my 2. B is my 2. So B is my 2. And now I am taking this is less than what number I can take is 2 point say 2 point say any number if you want. Okay. Say 7. Okay. I hope this is clear. So 2 point say not 7, say 2.9. Okay. So 2 is less than equals to 9. Yes, indeed. And I know if I take, so this is my B, as you can see, and I am taking this whole 2.9 number as C square. This means C will be my root 2.9. Yes. Yes, as C belongs to the real number set. Yes, this belongs to the real number set. Indeed. Okay. Now what? As I took C is equals to 2.9 accordingly. So if you compare A and C, A is this one, C is this one. So if you compare them, 3 and 2.9, 3 and 2.9, not so So if you compare this pair AC, this means A is less than equals to C. A is less than equals to C. I am comparing this pair. If this belongs to R, if this belongs to R, then I might say that it is my transitive. If this happens, if okay, there might be some chance that it is transitive. If I show that A comma C does not belongs to R, then it is not, definitely it is not transitive. Let's try to show this. So I took C square is equals to 2.9. Okay, this means C is equals to root 2.9. Okay, so now I am going to show this one. Okay, so if let's say if A comma C belongs to R, this means A must be less than equals to C square. If you see that A is my 3 and C square is my 2.9. Does this true? No, not true. So this means we took whatever the assumption, our assumption was wrong. So this means A comma C does not belongs to R. As you can see, if it does, if A comma C belongs to R, this means this will happen. This means this will true. But as you can see, 3 is not less than equals to 2.9. Yes. So this means the initial assumption was not correct, means that A comma C does not belongs to R. So we showed that A and BC belongs to the relation. As you can see, 3 comma 2 and 2 comma 2.9. Sorry, not 2 comma 2.9. It is root 2.9. So 2 comma root 2.9 belongs to R. A, B belongs to R. B, C belongs to R, as we saw. Okay, but A and C, AC, which is this AC pair, does not belongs to R. As you can easily see, if it does, if A comma C belongs to R, then this will happen, then this will also be true. But as you can see, it is not true. So this means A comma C does not belongs to R. So we showed that if A comma B and B comma C belongs to the relation, but A comma C does not belongs to the relation for some A, B, C, then we can say that it is not transitive. So it is neither a transitive. I hope you got the idea how we took this crucial C. The main thing is to pick such C that AC does not belongs to R, but AB and BC belongs to R. Okay, I hope this is very clear to you. Okay, let's move to next question. Now check whether the relation defined in this set, so the set given is 1, 2, 3, 4, 5, 6. As the relation defined as like this, the pair of AB such that B is equals to A plus 1. Okay, is reflexive, symmetric or transitive? Okay, first of all, let's list out all the pairs. So taking A and B both are coming from this set. So taking A as 1, B will be my 2, A2, B will be 3, 3, 4, yes, 4, 5, yes, 5, 6, yes, and A can be 6, yes, 6, 7. But if you see, if A is 6, then B will be 7, but B belongs to, but we know that B must be in the set, this set. But as you can see, 1, 2, 3, 4, 5, 6. But as you can see, B is equals to 7. 7 doesn't belongs to this set, given set. So this pair will not be in our relation. So we don't write it. So the possible pairs are 1, 2, 2, 3, 3, 4, 4, 5, 5, 6. Okay, I hope this is very clear to you. Now what? Now, as you can see, what you can see, it is quite clear that for reflexive one for reflexivity, we know if my relation R is from A to B, or the subset of A cross B, then take any element, then the pair with itself must be in R. Okay, for every A belongs to A. So here A is what? 1, 2, 3, 4, 5, 6. So this means 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, all. So take this, every element in this set. Okay, then the pair with itself must be in there for every element in this set. So is this happen? No, as you can see, 1, 1 is not there. Any of these elements aren't there. So this is not reflexive. Okay, for symmetric relation, what we need? We need that if AB belongs to R, if AB is in the relation R, then BA also in the relation R. Okay, so pick 2, 3, this, pick 2, 3. So 2, 3 belongs to R. This means then 3, 2 must also belongs to R. If this happens, then we might say that there is a possibility that it might be symmetric, but this doesn't happen. This means it is neither symmetric. Okay, so it is neither symmetric. Now for transitivity, it is quite clear. Taking 1, 2, 2, 3 as my AB and BC pair, then 1, 3 must also belongs to R for from transitivity rule. But as you can see, 1, 3 does not belongs to R. As you can see that these are the only possible pairs. So from this I can say that it is neither reflexive nor symmetric and nor transitive. Okay, I hope this is very clear to you. Let's move to next. Okay, the fourth one. Show that the relation R in the set of real numbers, the set of reals. Okay, set of reals defined as this. The set is defined like this: A comma B such that A is less than equals to B. Okay, so is it reflexive? Yes, as the question says show. So question is already answering that it is reflexive and transitive but not symmetric, but we need to show. So how we are going to show? It is quite easy. For reflexivity, what we need to show? A comma A belongs to the relation R for every A belongs to the set of reals. Okay, this means we know what we know, that A is equals to A. Yes, so from this I can write that it is true. What I can say? It is true to write A is less than equals to A. Okay, so this means by definition I can say this implies that A comma A belongs to the relation R. Belongs to the relation R for every A belongs to the set of reals. Okay. Okay, so we know this for any real number A. Okay, I hope this is clear. So it is reflexive as we showed. Now for symmetric relation, how we are going to show it? Sorry, for symmetric relation, how we are going to show that it is not symmetric? To show it is not symmetric, what we need to show what? Not symmetric. To show not symmetric, we need what? We need such AB pair which is belongs to the relation R, but BA does not belongs to the relation R. Okay, I hope this is clear to you. So if you take A as 1 and B as 2, as you can easily see that A comma B, so as you can see 1 is less than equals to 2. Yes, it is true. So this means 1 comma 2 belongs to R. But if you write like this, is it true? Not true. Not true. This means 2 comma 1 does not belongs to the relation R. Okay, relation R. So this means it is not symmetric. Okay, I hope this is very clear to you. Now to prove it is transitive, how we are going to say that it is transitive? Okay, so if it is transitive, let's go by the definition. So the transitive relation definition is what? If AB and BC pair both belongs to the relation R, then AC must also belongs to the relation R for every A, B, C. Belongs to the set. Which set I am talking about here? The set of reals. Okay, because R is my subset of R cross R. Yes. Okay. So AB belongs to R. This means A is less than equals to B. Yes. As well as B is less than equals to B, as it is already given, or we already assume that AB and BC belongs to R. So this means that A is less than equals to B and B is less than equals to C. So from this and this inequality, I can say A is less than equals to B, and as we know B is less than equals to C. From this you can easily see that A is less than equals to C. So from this you can say it is A comma C pair belongs to the relation R. Yes, so it is transitive. I hope this is very clear to you. So that's it for today. Thank you. We will meet next time. Thank you.